Hi all, welcome to Learn Code Repeat. So today we'll be looking at the day 14 of the LeetCode problem. The problem is house robber and it can be solved using dynamic programming, and we'll check that approach. So let's look into the problem. Okay, so the problem says that you're a professional robber planning to rob houses and each house has a certain amount of money stashed. The only constraint stopping you from robbing each of them is that adjacent houses have security system connected and it will automatically contact the police if two adjacent houses were broken into the same night. Given a list of non-negative integers representing the amount of money of each house, determine the maximum amount of money you can rob tonight without alerting police, right? So in short, we have to see that this array contains the amount of money in each house and you cannot rob the adjacent houses on the same day. So we have to check in the non-adjacent houses what is the max amount of money that we can accumulate. Okay, so if you check here, right, in the question, right, there are some hints, right? One is determine the maximum amount of money. So whenever a maximum amount of money is asked, right, or a maximum amount or minimum amount that you can get, right? So basically it's the question is saying that you need to optimize the solution to get the best out of it, right? Whenever such kind of questions is asked, right, one of the hint is to use dynamic programming. Okay, so here when you read the question, it says if you don't look into this particular part, right, get the maximum amount of money, and if you just look into that the array is non-negative and you need to make sure that the two adjacent houses are not broken at the same time, right? So if you directly go with non-adjacent numbers and add it, right, let's see what happens in that case, right? So here if it is 1 and 3 it is 4 and 2 and 1 it is 3, so max of both, right? So that means I'm adding odd numbers and adding even numbers and checking the max of that, right? So in this case it will work, it will give you 4, which is the correct one. Similarly in example 2, right, if I check, so if I add all the odd numbers, right, so 2 plus 9 plus 1 is 12 and 7 plus 3 is 10. Between 10 and 12 the max is 12, so in this case also it works, right? However, let's take one more example, right? So the first two example we looked at, let's take this third example, right? If we go by odd and even number addition, right, so 2 plus 7 is 9, 9 plus 3 is 12, so here odd is giving me 12 sum, and 10 plus 2 is also 12, so even is also giving me 12 sum, right? So based on that odd and even calculation we would have got 12 as the max amount. However, if you see, if I just add 10 and 3, then I will get 13 as the max, and these two are not adjacent, right? So that means we cannot go with the odd even calculation. We have to check which is the best possible sum that we can get, which is not adjacent, right? So that's where dynamic programming comes in, right, where at each step you have to check what is the best available option for that particular step. Let's take the example of Fibonacci sequence, right? So in Fibonacci, right, fib of n is fib of n minus 1 plus fib of n minus 2, right? So if I take for example fib of 5, right, it will be fib of 4 plus fib of 3, right? So what I'm doing here is I'm breaking down, instead of calculating the whole fib of 5, I know that my fib of n is basically the addition of my previous number and the number previous to that, right? So n minus 1 and n minus 2. Then I need to again break down n minus 1 and find out what is the value of n minus 1, and similarly for n minus 2. So what we are doing here is we are breaking down the actual problem into a sub problem and then trying to solve for that sub problem, right? While solving that sub problem, if we make sure that the sub problem is solved optimally, then overall the problem can be solved optimally, right? We can get the best answer, right? So this is basically an example of recursion, right, that we are doing here. So in this case fib of 5 will be 0 1 2 3 5, so 5 will be the last answer, right? And a recursive solution for this will be this. So initially we are returning 1 and 0 if n is 1 or n is 0, so that we break the recursive call, right? So this is the initial base condition, right? And then I just need to recursively call fib of n minus 1 and fib of n minus 2. That will give me the final answer, right? So this is one way of doing it, right, where I'm breaking down the problem into a sub problem and then only solving for that particular sub problem. However, in this, right, if you see, for fib of 5 I'm calling fib of 4 plus fib of 3. Then again for fib of 4 I will call fib of 3 plus fib of 2, right? So that means fib of 3 is getting calculated again for fib of 5 and also for fib of 4, right? So this is a simple calculation, so it's fine, but imagine that if it's a recursive tree and it's a complex calculation and you're calculating the same thing again and again, right? So that's not an efficient way, right? So the other way of doing that is if we can cache that calculation, somehow, so that that calculation is not getting calculated again and again, and if it is present in my cache, I can simply return the cached value, right? So that approach of caching prior calculation is called memoization. Okay, it's not memorization, it's memoization, and the solution with that approach will be something like this. So here with memoization, what we are doing is again n1 and n0 we are returning either 1 or 0, and then I'm declaring a fib array which is n plus 1. The reason why it's n plus 1 is because we are starting with 0 and then 1 2 3 4 5, so it's n plus 1. So fib of 0 we know it is 0, fib of 1 we know it is 1, and then I'm simply doing a for loop from 2 to n, and fib of I, that means the ith index in my fib array, the value for this will be I minus 1 index of my fib array plus I minus 2 index. So if you see here, right, we have already calculated I minus 1 and I minus 2, and we are not again recalculating the value for I minus 1, right? So we are utilizing that calculated value and doing it here. So overall, if you see, even though the additional space we are using is fib of n or fib of n plus 1 to be precise, but we are saving time in doing the calculation, right? And at the end I can simply return fib of n, which will be the value of this n, right? So that way it will be faster because I'm not calculating it again and again. So this is a short description of dynamic programming, how we can do, right? So how we can utilize this approach in our problem, right? So let's take this example, right? If we break this problem into sub problem, right, then at each step we have to see what is the best value we can get, right? So for example, at step 1, right, that is index of 0, right, I can only have the best value as the same number, right, 2. So let's take that same index value here, 2, for index of 0, and at index of 1, right, what is the best value that I can have? So what is the precondition? Precondition is that I cannot get the adjacent houses amount, right? So when I'm at index 1, right, I cannot add my previous index, that is my adjacent house amount, right? And the house prior to that, there is no house, right, prior to that, because it starts with 0, and here I am at index 1, right? Now at this point, right, at 10, right, when I'm at index 1, what is the best value that I can have, right? So the best value I can have is either I can take this amount and add it to my non-adjacent previous value. So in this case there is no non-adjacent previous value, right? So either I can take that, or I cannot take this at all and stay with my previous best value, right? Previous best was 2 and this value. So in short, what we are saying is take the max of these two, between these two, whatever is the max, right? So between these two, 10 and 2, the max is 10. So I'll keep 10 as my first index. Okay. So if I consider this as my DP array, DP is for dynamic programming, so we just initialized it as DP. So DP of 0 is whatever is my num of 0, and DP of 1 is between num of 0 and num of 1, what is the best value that we can get, right? So remember, here we are doing num of 0 and num of 1 because we are not adding both the values, right? We are just saying that either I can rob this house or I can rob this house. So at this point, which is the best option that I can have? So to check that, I can simply do a max of those two houses, right? So in this case it will be 10 is the best option, so I'll go with that, right? So here the value will be 10. Now for the third house, right, when I'm at third index, right, how can I check whether I need to rob this house or not, right? Is I can either pick this. If I'm picking this, then I can go with previous non-adjacent best value, right? So at second index, what is the previous non-adjacent best value? It will be the index which is minus 2 of this, right? Because minus 1 will be adjacent index, right? So minus 2 of this, it will be this at index 0. What was my best value, right? So if I'm picking this, I can also add my index of 0. So 7 plus 2 will be 9. So either I can go with that, or I can go with my previous adjacent value. only my previous adjacent value. Whatever is max between this and 7 plus 2, I'll go with that. So between that 10 and 7 plus 2 is 9. Between 10 and 9, 10 is the max. So I'll go with 10 for this particular index. Okay. Similarly, I can check when I'm at index 3, the value is 2. So at this point, index 3, I can either pick up this value plus my non-adjacent best value. So this is 3, 3 minus 2 is 1. So at index 1, my best value was 10, and 10 plus 2 is 12. So either I can have 12 or I can go with my previous best value. Okay, previous best value was 10, right? So between 10 and 12, 12 is my best value. Similarly, for last index, I can either go with this plus my previous best value, which is non-adjacent. So previous best value, which is non-adjacent, is 10 here. 10 plus 3 is 13. So either I can go with 13 or I can go with the previous adjacent value, because I am not considering this index. So I can directly go with previous best value, whatever it is, right? So in this case, the previous best value is 12. So it will be max of between 12 and 13, which is 13. So at the end, my output will be 13, right? Which is what we are expecting here, right? So if you see the function, right, that we were using for dynamic programming, right, like the way we use for Fibonacci, where we were doing n minus 1 plus n minus 2. So here the function is that for my sub problem, I will check either if I am considering my current number, then add also the previous non-adjacent number that I calculated earlier, or don't use the current number at all and go with my previous best value, right? So that's what we are doing here. So I'm checking the max of if I'm considering my current number and my previous non-adjacent number, or my previous best value. The max of these two I am storing in my current index. So that is my optimization that I am doing at each level. So I've broken down the whole problem into a sub problem, and at each step I am calculating the best I can get at that step. So that way, at the end of the step, I know that I will have the best output or the max value, right? So at the end, when I'm returning, I can only return the last index. So in this case, dp.length minus 1 will give me the last index in that array. Okay. Now in this problem, the complexity will be, the time complexity will be O of n, because I have to go through the whole array. So I have to traverse through each element. So it will be O of n. And the space complexity will be, since I am creating a DP array of n, it will be O of n. So space complexity will also be O of n. However, we can reduce the space complexity into O of 1, right? Because we are only interested in my previous element, previous best element, or the non-adjacent previous element, right? So we can just keep two variables and we can reduce the complexities. So let's look into the code and see how we can solve it using a DP array with O of n space complexity and also with O of 1 space complexity. So the base condition before we start, right, if nums is null or if it is 0, right, here it's given that the length can be 0, right, so we have to take care of that as well. So if nums is null or it is 0 length, then we have to return 0. Similarly, if it is only 1 length, then we don't need to do any calculation. Whatever is the number in that, we can return that. And if it is only 2 length, then we can just check the max between those two and return that, right? So let's take care of that condition first. Okay, so now we have taken care of those conditions. Now let's declare our DP array. The length will be same as nums length here in this case. And we know that DP of 0 will be same as nums of 0. And DP of 1 will be my max of nums of 0 or nums of 1. Okay. So that means at this point, right, at this index, 0th index, it will be only nums of 0, the best I can have. At first index, the best I can have is either 0 or my current number. Between either of them, whatever is the max, that is the best I can have, right? So that's what I'm doing here. And then in my for loop, since I have calculated for 0 and 1, I can start with second index. And you can simply do dp of I equal to math.max of, if I consider my current number, then current number plus the previous best non-adjacent number, right, which will be I minus 2. Or I should not consider my current number. In that case, I can go with my previous best number, right, which is dp of I minus 1. Okay, so after this loop, the last index will have the best value, right, which is dp of minus 1. So let's see whether it works fine. Okay, let's submit. So this is working fine, and if I go into more details, it runs in 0 milliseconds, so we are good here. Now let's edit the code, and instead of O of n space, let's do it without O of n space, right? O of 1 space basically. So let's see what we can do for that. So if you see here, right, we are basically only interested in two variables here, dp of 0 and dp of 1, and the same is being referred here as a more generic way, right? So I can declare, instead of my dp array, let me comment this out. I'll just copy the same thing. So instead of dp of 0, I can say int dp1, which is num1, and int dp2, which is max of num0 and num1, and I can start with equal to 2 as less than nums dot length, and let's say here int max equal to dp2, and I'm using max here to store the max value, and this will be nums of I plus dp of I minus 2 is nothing but dp1 in our case, and dp of I minus 1 will be dp2, right? So once I've calculated the max, I need to make sure that my dp1 now points to dp2, and my dp2 now points to max, right? So that way I will store my max value in my dp2 and dp2's value in my dp1, and I can move ahead, right, in my array. So at the end, my max will have the maximum value that I can have, right? So this way I can use only 3 variables instead of a dp array, and solve this in O of 1 space. Let's run this code, submit it. Okay, so this is also accepted, and the runtime is again 0 millisecond. That's it for this video. Thank you all for watching. If you liked the video, please hit the like button and do subscribe to the channel. And if you have any questions regarding dynamic programming or this approach, please comment down in the comment section. Thank you.